sharing my. Okay, so we're going to start the session with Tommy giving us the annual update on PMR2.
Yeah.
Thanks, Tommy.
Yeah, so I am Tommy, the developer of the software called PMR2, which you guys might know on the Lithium repository. Right? Yeah. I'll show you more later. So, as I said, in-house of Lithium repository, you can build that if you want to. And now we migrated last year, May, moved our hosting to Amazon EC2 for latency reasons. So because we've had people telling me that they're accessing from Europe and the repository is really slow because it's open upload. So it's now up at EC2. You guys should be able to get to it much quicker. And we now also provide a mechanism to store models and associate that data in Gits. And another thing is that in our background, first we have the presentation overview, we call them exposures, and that's driven by a set of plugins. So we were displaying some models, just set some specific plugins, do it ML, same thing. And specific metadata in RDF is all index, and we also have code service in collection based on all holding points. So what actually happened in the last year is that, as I said, like migration to Git, because people have demanded that for Git support, but mainly because GitHub has essentially won the mind share for all distributed working ecosystems, and also in the interest of standardizing documentation across the API and pretty much around this area, we decided to go with Flow and went with Git. So previously, all the workspaces in the Lithium repository is backed by Mercurial. Of course, that means that migration is done. So all the workspaces have been migrated from Mercurial to Git, including all the embedded workspaces. So micro models are all okay. Because micro use a lot of embedded features of the embedded workspaces to glue this all together. So his work is still on. Migration has been lost now. And we now provide better metadata indexing, so we can have searching driven using ontology-based metadata. This started with the recorder effort, and we have integrated the basic features of recorder is now integrated into PMR2. So we can do searching based on search terms in might as well. I'll drag this here. And here we have the search box here. So you could do something like wait for the to show up, select the search term, see that it brings up this gene ontology identifier for this particular term. Search will take some bit of time to get back the results because this is a lot of because this search term has many subterms, so you can see that once the results come back, you can see that voltage gated has emission activity, and inside there are like these things that are annotated. Same thing with calcium, and I think we'll down there. So like these actually bring you back to the model, the raw model currently, because that's what's now dealing with. But in the future, we'll make it prettier. As I said, basic searches without concepts. So those of you interested in comments and annotations, I probably come up to you. What we can do to make searches better and the method and the cement make everything just better. Okay. So these are lists of ontologies currently installed and available like PMR2. But this is, as I said, this is basic implementation, at least because I think of it as a chicken and egg problem. Previously, when we don't have the search engine, we'll kind of see that metadata is kind of pointless because we can't really use anything with it. So we have to come up with something to at least bootstrap it. So that's what the search engine achieved. You can see that there's actually people have annotated the models, and we have basic search terms, metadata triples that are in the triple store that we can start building queries of, and in the future, once we get more of these, we make concept annotations and make it easier for people to find models that they need when they want to start combining models together. Yeah, I kind of jumped. Another thing is that quite often when we do software, we develop like different groups that develop software in many different languages. For instance, PMR2 is done in Python, but quite often we have search engines that other groups have developed using Java. But means that communications between the two pieces of software can be problematic. But we have these things called web services, so that provides a more generic interfaces that two different pieces of software can communicate with each other. So these are the things I want to see. Again, I jumped the gun, but PMR2 has new sets of web services that are done using the collection JSON format. And this is delivered using developed using the hypermedia methodologies, which means that a single resource in PMR2 identified by its URL can have different representations. So there is standard representation, which you would see by pointing to the repository through the through a standard web browser, like so. However, you want so you navigate much like pointing and clicking. However, we can copy this link, point it to a demo collection JSON browser. It will fetch the same content, but using JSON. Hopefully it'll work. There you go. So here's a list of models. Much like this list here, but this is a third-party service that is still consuming the web service that PMR2 currently provides. And it's fully interactive.
Are there names of the papers?
Yeah, that's generally the name. These are models that are essentially named after the papers. Yeah, so here we can see that again through the web service we have the basic data return and the set of different sections. I don't think any of these will actually be getting back into them, but that's because the migration is still in progress. But if you actually look in the raw data through the if you develop in the client, you can actually see that it will provide JSON that's not in the collection JSON format. And naturally, the searching interface through for the phone, and it's still using the old format, but this is work in progress. And presentation views, as I said, the functionality is defined by add-ons, and this includes such as some of code generation, browse the repository, get the model code, and see Python, also has how it is. And another work in progress, we have the WebGL-based UML open sequencing browser. And actually, before I jump that, this is actually it demonstrates that there is this thing here, and so this is a demonstration of WebGL viewer. This is derived directly from a EX file. So 3D zoomable, and the WebGL is dynamically generated from this particular source. So actually, that is probably bigger than that. Yeah. So it's generated from this particular file. Other future plans, access to unique ontology and PMR2, so for searching general information. And other thing is, since we have all the triples indexed by the triple store, we would like to provide users ways to compose their own Sparkle queries to get back search results in the way format that they desire. And naturally, refining the web service stuff, which you is really interested in. And of course, integration with other web services, such as the service side. Question.
What do you think of this Cats2M project if they implement it? Is there any difference from your point of view?
Because again, if they consume the web service, what's that? Okay. If they consume the web service provided by PMR2, if they also download the entire history, then it's a way for people to consume data. So it's something I don't see a problem with. That's what you mean. Another thing is I'll be partnering with okay.
Probably saying the wrong thing. Is it possible some simple way that the service is trying to provide is way by using will it be more simple, or maybe with the broad range of this aspect in general?
It's I mean, if you want, because one yes. Yes.
Metadata. Does that end up being required as the CellML file is separate?
We use a couple things. Ideally, I want them to be separate because it makes referencing easier, it makes exporting a lot easier. Because embedding the file, you got to extract the XML or the RDF from the XML, and then you got to. It's more problematic, in my opinion.
I guess we need somewhere to make sure they stay in sync.
Which is why we also use a version control system. So if we have the best practice is that whenever you update the metadata, you also, before you commit, building a chain set, you also make sure that the model is updated, then you make a commit, so it will all be in sync. So every chain set with the let's turn I had the problem like the provenance of the changes are all with between the model and the metadata should be maintained.
Yeah, I think we just need to make sure that all the tools
load
both at once and make sure that
Yeah, the version control is a powerful tool to ensure the provenance information is maintained.
Question.
Yes.
Have you ever come across a requirement to have multiple language translations of models like XML?
The language translation from CellML to Python and C is all
I'm
done.
talking about human languages, like the parts of the model for consumption in different cultures and countries.
Not yet.
Why do you say that it's so?
But if you're talking about the UI, Home is it does support multiple languages, just that I need translators. No more questions? Alrighty.
Okay. Hopefully this will keep working. So let's go and tell us about the latest developments in open core to main CellML creation, editing. So, as you just said, I'm going to tell you about the first core and the native development of the first. So, that's the picture. Why? Because the last year we implemented a feature that is existing in core, which is kind of piece of CellML software that we develop and future when we contribute to open core in the future. So, for those who don't know, open core is a cross-platform computing environment for organizing editing, editing, and in the future analyzing CellML files. It is an open source project. It is currently released under the FAST license. It has a very simple website, opencore.ws. It contains some information about the user documentation as well as developer documentation. So basically, anything you need to know about core is available on the website. Everything, all the source code is available on GitHub. That have web address. Basically, if you want to look at the source code, you can do so, no problem there. OpenCore is currently supported on Windows, Linux, and Mac. And it can be used either as a command line tool or through a graphical user interface. So today, I will mainly demonstrate the graphical user interface, but you can use a command line tool as well. All the features that are available in OpenCore are available as a plugin. That is very important because that means that if there is a feature that is not currently available and that you want to add that feature in OpenCore, when either you can develop a plugin for it or you can ask us to develop a particular plugin. We will illustrate that in a minute. And as you may expect for software projects such as OpenCore, we do use quite a few third-party libraries, including NPM. This is the library for those who are aware. That basically allows you to compile C code, for instance, on the fly. And that's the kind of thing that we use when we want to actually run a CellML file. When you want to run a CellML file, you go from CellML to C code, and then that particular C code is compiled using the LLVM library. And that allows us to actually run the simulations. So since last year, so since the last meeting, OpenCode 0.3 has been released. So there are different features compared to the latest snapshot available at the time that have been implemented, so such as creating a new file, kind of. So you can create nowadays CellML file, CellML file, or even a blank file. This will not look like a big feature in itself, but because in OpenCore we have different ways of actually editing files, etc. That did mean to be possible to work on the infrastructure of the software. Then, for people who are interested in developing plugins, we actually created some sample plugins. So different plugins, such as sample, this one, they can just as an addition. So yeah, A plus B returns value that. Then some sample tools plugin, sample view, and some sample video. I will explain very quickly the kind of thing that we can do with this. But the point here, I think, is that anyone who is interested in creating plugins, well, you can have a look at those ones. That would basically allow you to create any kind of plugin that is currently supported by OpenCore. Then another feature that was implemented in 0.3 is the CellML export to a user-defined format. So in this particular case, we do take advantage of the CellML API. So that is the reason we provide files for exporting to C, for translation, MATLAB, and Python. However, my personal take on this is that well, it doesn't look great. I mean, the export that is currently generated doesn't look very nice, in my personal view. So what we are thinking of doing at some point is to generate some vector code from that. Then something which was done in the raw CellML view, we can mention that very quickly in the discussion later on, but now we can generate equations. We can render the mathematical equations that are available in the CellML file. And as you may expect, there are numerous improvements and a few fixes here and there. As it happens, those are the kind of the different things that have been done in the code 0.3. So the green bits are things that have been added, yellow bits are things that have been improved, and the red bits. So quite a few things indeed. And what I will illustrate in the picture are mainly the raw view and the raw segment view. Those are for editing files in general. Then, since 0.3, which was released some time around about than that, when there have been a few of those things that have been done, such as checking for official releases and snapshots for OpenCore. So basically, if you run OpenCore and we do release a new official version or new snapshot, then you will get told about that, as long as we allow to be told about it. Since initially we were supporting only 32-bit Windows, now we do support 64-bit as well. And as those of you who use Mac, we know that ultimately has been released, we also support that particular version. However, because Microsoft now has officially dropped Windows XP, well, we don't choose Windows XP here. We don't support the Windows XP anymore. And because I don't like Vista, we don't support Vista either. Nobody wants to do that. Then there have been lots of improvements to the GUI and responsiveness of the CellML annotation view. Some of you may remember that I demonstrated that particular view last year. So a lot of work has been done on that one. Make it easier to use, more. Then some work from David Brook. Some of you may know him from the ABI. Has been on the data store. I will illustrate that in the demonstration later on. And the idea of this particular work is that we can currently export simulation data to a CSV format, a comma separated value format. But thanks to David Brook, at some point we will be able to export to other formats such as biosingle and ML. Not only export, but eventually we will also be able to import data in a format such as biosingle and ML. Then a big chunk of work was done on the CellML text view. that element text view is basically a way to kind of be backward compatible with people with the software core, and in particular the core format. Again, I will illustrate that in a minute because this is a big improvement in OpenCore when it comes to actually creating and editing element files. And again, numerous improvements and a few fixes here and there. So this is currently what has been done for the current snapshot, and I guess it's important to say that this particular snapshot was released a few days ago, well, last week actually, may actually become the official next version of OpenCore. So people who are interested in OpenCore, I would highly recommend downloading the latest snapshot and give it a go and tell me what you think, and these are, especially there are bugs or anything like that. But otherwise, most likely, within the next couple of weeks, definitely before the end of the month, there will be OpenCore 0.4. So, yeah, as I said earlier, I will use this particular aspect. So, data store framework that Daily Group has implemented, and also the CellML text. And I think that's pretty much it. So now this is our mission screen. Okay. Oh, okay.
Sorry, Max probably wants to see the demo, so we'll just try and get it back on. Let me see.
Let's try that. That's okay. So now I'm going to demonstrate OpenCore, well, the latest features. So when you start OpenCore, it does look like this. So as I said, everything is a plugin in OpenCore. So for instance, this bit is a plugin, this one, etc. Even the head is a plugin. I won't go back into this because people who were here last year will know already. They will already know about this. But what I want to do here is to show some of the new features. So for instance, if I open this particular model, and I can go to the raw element view like this. As I said earlier, we can now render mathematical equations. So what you are seeing here is the raw element view. So we do have syntax alignment to make it easier to understand. But certainly here, people probably can tell that it is some MathML code. But you can see that if I move the mouse here, you get the equation renders like this. And for instance, if we go to another equation that contains some more interesting stuff, so maybe, yeah, something like that. So you can customize the rendering of the equation. So you can, for instance, use a script like this, so you can see that now it's underscore n. And then you can also do Greek symbols like this. So what if OpenCore recognizes what that particular plugin recognizes that there is a Greek character or whatever, then you can render it as a Greek symbol. Like that. So that's what you have for with regard to the raw element view. Then we have the CellML text view. So basically this is exactly the same contents for that particular model, which is a 1962 model, except that it is rendered in a way that does respect the core, the format that is used in core. So this is a format that we believe is easier for people to actually modify rather than having to modify the raw element text as such. So as in the raw element view, we can also render mathematical equations like this, which means that while if you modify the equation, we see that automatically updated. And in that context, what I'm going to do now is that I'm going to create a new element file, like this, and we are going to implement a very simple model, which is the Vanderpool model. So for those who are not aware, this is basically a simple oscillator, and it contains a couple of bodies, and this dx equals y, and zero is equals this. We have three initial conditions like this. So very simple model, and if we go here, so you can just create here, okay, let's create my model like this, why not? And from there, what you need to do is specify some, or declare some variables like this. So let's create X. At this point, when everything must have a unit associated with variables or constants. Here, in the interest of time, we set everything to dimensionless, makes it much easier. I think it's this. So from there, yeah, we have another one. That's this. Then we have the mu, dimensionless. Yeah, you're getting there, you're spoiling it. So basically, here we want to do dxdt, and as Peter hinted, but we need the t, and but yeah, here we can still write the equation to start with. So basically, we have mu like this times 1 minus sqr of x, and times y, I believe, minus x. And you can tell that here the equation is not correct, and that's because, for one, I didn't put the unit for that particular constant. So as I said, everything must have a unit, every constant or variable. And as Peter said, we do need indeed to specify the variable of integration that we want to use here. So we do it like this, and we initialize it to 0 like this. So at this point, oh, I forgot to do something. Yeah. So that's a good thing. I mean, if I try to validate the model, then the view will tell me that something is missing, and indeed, what I completely forgot to do is this. So I need to specify components as this. And, so from there, yeah, everything is fine. So at this point, I just created my very simple CellML model. All I need to do now is to actually save it. From there. Sorry? Oh, yeah. Oh, sorry. You're right, yeah. So that is a Y one. Thank God I do have Peter to tell me what I'm doing wrong. So I see. I think that is correct. Is that correct, Peter? Yeah? Okay, good. So now, okay, let's create my model as is. I can put .CellML or whatever, it doesn't matter. So, okay, I have my CellML file as is here. If I go to the raw CellML view, you can see that, yeah, this is the CellML code for that particular model. Again, I think we probably agree that it's much easier to do it here than in the raw CellML view. But anyway, so now we do have that equation like this model with these two ODEs. Now at this point we can go to the simulation mode. There are different things here. One is that we have the graph analysis, so we can create several of them. You can create as many as you want. Here we have all the different parameters that make up the model, and from there we can also specify different things about simulation. So for instance, here we want to run the model maybe for 50 milliseconds or whatever. Here we have to specify how often we want simulation data to be generated. Here we have access to different solvers. So we have here access to CBOD by default, forwarder, development, and run second order and first order. These solvers are basically listed depending on which type of model you are working with. So if we are working with an ODE problem, we'll have access to these solvers. If you were to work with a DA problem, then it would be different solvers, etc. At this point, we also want to specify exactly what we want to plot and what we want to see in terms of simulation data. So for instance, on the first graph, we might be interested in plotting x against the variable of integration. On this graph, you can see that there is a blue bar here. We might want to plot y against time. And then on this one, why not plot y against x? So here we are all set to run the simulation. And here we go. So this is what we get when you run the model. At this point, you might also want to export to a CSV format. So that's what I said about David Brooks' data store framework. So again, we have the drop-down list because at this point, we have only one data store available, which is CSV. So we can export to that particular format. But once we will have the biosignal ML1, for instance, what we will have is that not only the CSV entry, but also biosignal ML and any other kind of data store format. So here we can just write data. It's CSV one. And that means that if we open that in something like Excel, then you will see all the simulation data, and you can do whatever you want with the data. So I think in terms of the new features, that's pretty much that. As I said, this is probably the main feature in OpenCore, as well as the CellML annotation that has been reworked quite a bit well. In the interest of time, I think I will just stop here.
Corey was asking about multilingual facilities. You know, just talk about how you show the French version.
Oh, sorry. Yeah, okay. So, indeed, OpenCore is multilingual. So at this point in time, it's only French and English. But let me show you that where we do have some stuff. So, for instance, here we can see simulation solvers, etc., graphs and parameters. So in a minute we are going to start how we do say that in French. We say simulation, solver, courbe, and parameter. But basically anything that can be translated is translated. So for instance, with the solver, you can see that by default, this is that name, maximum state, maximum number of states, etc. What is that being translated in French? So everything that can be translated in a different language is being translated with switch languages like this.
Does Qt give you that facility?
Yes. So basically, within Qt there is a means to actually translate everything you want to actually be able to translate. So it's completely up to the developer to decide. Okay, I want to be able to translate this bit of sentence or whatever. So yeah. And that means that if you want to translate that to German or whatever, that's no problem at all. It can be done very quickly. You have to provide the translations. With regards to very quickly about checking for updates, as I said, if you are connected to the internet, it will check whether there is a new version available. So by default, it will check that at startup. But if you don't want, well, you can just unclick. It will also include snapshots if you want, so it's completely up to you. But yeah, that's pretty much that. I guess something that I'm just looking at the interface here, but if we reset everything, what you can do is also play with that wheel. The purpose of that wheel is to actually slow down the simulation. So that may sound a bit silly, but for teaching purposes, it can actually be quite useful sometimes. So you can see something like this. And the other thing that I didn't quite mention, but I guess it's kind of obvious, is that you can pause the simulation. So I'm running the simulation as is. I can pause it and modify parameter values. So for instance, if I set it to 5 as is, then I can resume the simulation and see what happens. So that can actually be quite useful again for teaching purposes. So I think that's pretty much what I believe I already very lot of time. Oh, yeah, I forgot about that. Sorry, very quickly, that's what's coming up. CellML support, very, very important to us. Python support, hopefully before the end of the year, and some CellML annotation. We mentioned composite annotation. That's something that we want to be able to support within CellML, OpenCore. CellML takes you by proper CellML validation. I don't have time to go into the details of that. Single cell view. We want to have a few more features that will be very useful. For instance, support for multiple runs, as well as to be able to save the new state of the simulation. CellML export. When I mentioned the CellML export to C, for etc., but also to tech and MS Word. That should be very easy to do. And MS Word, it's future, but still possible. And if you are curious, you can see the current feature request, etc. at this web address. And yeah, all that core wouldn't be possible without Dan support and Peter support, and also Dave knows for desktop. I think now that's easy.
Sure.
Yeah.
So along the same lines as what I just commented, if you kind of grab a file of the PMR,
Yeah.
does it create a metadata so that that's what the file that you're annotating?
So okay, at this point in time, when it comes to CellML annotation, all the annotation is actually saved within the CellML file. So if you are getting a CellML file from the hardware, it will be locally within your local copy of the CellML file. So I think at some point what we probably want to do is to actually save the metadata information elsewhere in a different file. I think that's what the combination facility might have more information on that, but I think that's probably what we want to do at some.
It would be good to get other people's views on that, but I thought it would always be useful to have the metadata as part of the settlement file. The whole thing. Yeah, but easier to extract it for the search. But okay. Do you agree, Gary? That's always.
Yeah, well, my hunch is just it would be easier to misplace it or overwrite it or do it wrong with someone else.
I think that the problem comes in when access control is different between your description of the model and the model itself. So it's fine for us because everything's available for everyone. But if you wanted to make your, let people know what you're working on without actually giving them your work or something like that, you want to keep the annotations separate. But within the PMR2 framework, it's easy to manage collections of pieces of work and combine archive.
The other problem with putting them all on one file is you've got to have syntactic agreement, right? So if you have multiple systems that want to share information, they would have to know how to find the metadata, right? Whereas if you put the metadata in a separate file, it's much more clear. If I want to search for files, all I need to understand is how to look through the metadata. I don't need to know how to parse them. That's a reason for keeping it separate. I think I'm arguing that you should keep the metadata separate from the original file. But links, obviously, you need to do something like GitHub and keep versions separate.
I think Mike wants to say.
I was going to talk about that tomorrow, but if you think about annotation as a description of something, then you can have multiple descriptions of something, and they shouldn't necessarily be tied to the thing they're describing. So we have a view of PMR, but it's a very PMR-centric view, and it's not the view that many other people would have. So from that perspective, putting it in the CellML file unnecessarily couples those two things together a lot of the time. And it's just as easy, because I've done this myself, for the annotation to get out of sync with the model, even if it is in the model. Because it doesn't mean you read it. So,
yeah, I mean, similar, the same concept, I guess, in the clinical models I will talk about a little bit later on. There are, I think, two types of metadata. One that really contributes to the knowledge that relates to the model, and one that is like a descriptor, including language translations and stuff. So you can take the latter out probably, but the former one, which is slightly coupled with the knowledge aspect of the model, I think has to be available to the model, like forms and everything.
I guess the point is that once we have said ML files, they'll become the master file. And then you can specify, both reading your CellML and the metadata.
Yeah, I don't like the idea of a master file because you have multiple master files depending on what the purpose you're doing.
But like Gary, I'm just worried about bits of information becoming difficult to keep track of.
I suppose you just need to make sure that if that metadata file does exist, then call loads it up.
Yeah, and so I think it's a software tool sort of issue to know about these things and keep them in sync or prompt the user to say, hey, this also has this other information. Are you sure you don't want to update it?
Or even just automatically, as soon as it's updated, it's no longer coupled. It's only coupled to the original.
Just that we have to keep reminding ourselves that this is the biologists, not the computer scientists. So we've got to keep on thinking about what is it that makes life easy for not.
Yeah, that's the tool that presents that view, not the underlying formats or files or where they're stored in the world.
It's for biologists who are using
Because even in the file, if you have a CellML 1.1 model, it's multiple files anyway. And so you have different descriptions of what those bits are depending on what level in the hierarchy you're looking at. So, I mean, open source is going to handle whatever the best practice is.
Maybe an analogy is when you go write a grant proposal, you take your CV or whatever, it's crafted with that proposal of it. You don't wander around with your proposal with your CV strapped to your chest all the time.
Yeah. Thanks. It's probably easier on this one, I think. We could have a network connection. What's going on now?
It's tangled.
It's so rich. It's back here.
Alright. So, I'm John Denari from the University of Washington, and Brian and I have a get together and talk a little bit about that. I'm in the Department of Biomedical Informatics, and so I'm coming at you with a little different perspective. And this is in a software update session, and I will talk about the SendGen software. I want to warn you that I'm using this time slot and kind of cheating a little bit, and I'm going to give you a broader overview of where we're coming from. Brian made a nice demo of SendGen on Wednesday, and I'm hoping most of you saw that. And we, either Brian or I can give demos at any time for the software. So this session will not be a demo, but I encourage you to go ahead and try it out with us or download it yourself. So instead, I'm going to give sort of a broader picture, and I'm pretty sure I'm very much preaching to the choir. At least that's my sense from who I've talked to so far. But I think it's very useful to do that because we're all emissaries, and when we go out and try to convince funding agencies and other people to buy into this vision, we should know how best to present it or how to present it convincingly. So one thing I did here is that I'm going to talk about when you're building, when you're carrying research with mathematical models and with biosimulation, do you build everything by yourself in your own house, or you borrow stuff? You build other things. And there's a trade-off. There's a very important trade-off. So you can either build models that are very fast, very accurate, very effective, but do a great job of modeling physiology or demonstrating the mechanics of all the kind of cardiac mechanics stuff we heard last week. But they may not plug and play with others. You know, the picture here is Apple products which don't interact with other products. In contrast to something like Git or other public shareable stuff that really works like Lego pieces. That's the vision. We want this to work like Lego pieces. But any given research team may not be ready for the Lego stage of their work yet, and that's fine. You may be in this private phase where you're really trying to figure it out and you're concerned about efficiency, and you're not concerned about sharing. And we shouldn't try to convince these people that they should buy into the standard. And we should only convince people that are ready to start plugging and playing with others. So again, this plays out as do we build an in-house. Well, actually, there's two levels of interoperability. One is that you develop an in-house library where you might have a single software project that doesn't play with others, that is built in a plug-in architecture so different software developers can interact. So that's one level. Versus actually going outside and using, if I'm at the University of Washington and I say I want to build a biosimulation model, am I going to go to Auckland and say I'm going to use the CellML standard? That's the next level of sharing. And then, just to reiterate to the point, it's always easier to test and publish about your own work. And it's much, much, much harder to get others to use the standard you develop. And that's what we're all trying to do, both the CellML group and our own research. So the reasons that you wouldn't want to use somebody else's stuff is that you're familiar with how to do it yourself. You think if I build it myself, I'll be able to tweak it exactly how I want it. I can customize it. You might distrust those guys down in Auckland. And even if you didn't distrust them, there's certainly a learning curve with understanding how this is going to work. So again, preaching to the choir, I think you guys know there's a history of different repositories for biosimulation. And the key here is that we should never imagine that we're going to be in a world where everybody's going to have only one way of doing this. It's not the case that one of these is going to win, the other are all going to disappear. They're all going to coexist. It's very clear. And so what my research group is interested in, and I think what a lot of, again, I'm preaching to choir, I hope, is figuring out ways of getting these things to plug and play together, to go back and forth. We've already heard some talks about being able to read in SVML models. The first talk this morning was very nice that way from the German collaborator. Okay, so does that make sense? That's kind of the vision there. Just wanted to put that out there. Spend a little time on that. And then I'll talk now more about SEMGen. Okay. So SEMGen is a kind of historically old project in that, I don't know, old in some sense. Max Neal is really the starting of it, well, Max Neal and myself, prior to 2010. So that's why we actually call the SEMGen 3.0, not 0.3. But the current project is in collaboration with Dan Beard's virtual physiological lab, who Alan mentioned as well. And our software. And as I said, Brian and I are leaders of that. So, again, kind of preaching the stuff you guys all know, is that when you're modeling, you're trying to answer some question about physiology or pathology. How does X work? And you're going to build some models and then match data and verify to see if your theory was correct about how X works. And X could be hypertension, which is one of the main goals of the virtual physiological lab. And in more detail, for example, you might be interested in the baroreceptor. And so then, for that example, you would build models perhaps aortic blood pressure, something like the work cycle, and circulation. If that's your question, the interesting thing to notice is that, well, okay, is there other work I can leverage that's out there that I could use to start with or supplement my current models or ideas? And if you look for, I think it's those three things, aortic blood pressure, baroreceptors, and circulation, this is a nice little table we built in a little literature search. And not just literature, but really looking for models. And these are all citations to papers that are mathematical models of the circulation system, of the baroreceptors, of the models that include one. So there's a lot of models out there. And so the goal is to allow researchers to figure out a way to understand these models without just sitting down and reading the papers and going through the equations and trying to replicate them, which, as we've heard, is very hard to do. So, how do we choose amongst these? Once you've chosen them, how do we build them up? How do we combine them? And then eventually how do we improve them? So, we're trying to support tools for all that, right? What can we do? Finding models, merging the models, and visualizing them. So, finding models, retrieving. Now, we believe, as you've heard other talks, that annotation is crucial for understanding and finding these models. And I will talk about composite annotations. That's come up. I'll describe exactly what that is. Then, model merging is the process whereby you say, okay, this is a great model, I like it.
But I only want to use part of it. Okay, so actually, you might want to extract out the part you care about, the set of equations that you want to use, and ignore some other part of that model. So you extract that out, and then you take that bit of code, or that map, or that component, and plug it into your model, and then generate code so you can run it on Open Core or JSON or biosimulation engine of your choice. And then this might be a little out of order now that I think about it, because really visualization comes before you do the merging, right? So you do a retrieval, you get a list of models you don't really still understand them necessarily. You might want to visualize those models to help you understand them. You also might visualize the final product as well. But in any way, it's often useful to look at these things. And so we claim that we've kind of done all of this to some degree. I'll say that our search is very rudimentary. We're happy to leverage off of other methods for doing search, but we believe that we've got good methods for annotation. And we're using a D3 visualization language that was throughout Cytoscape work, which is a very, very flexible plugin architecture for Java and JavaScript. Not exactly sure. I can't remember the language it's based on. For a wide variety of visualization methods. Okay, so I'm going to talk a little bit about composite annotation next, but to get there, I've got to talk about semantics. So, as I'll credit at the end of the talk, this is also work in close collaboration with Dan Beard, who was here last year, or 2 years ago, or both, I can't remember. And he is concerned about biological truth and ecology and physics for biology. And I'm excited here to to talk to Edmund Crimson about also the biological truth of chemical reactions, which we'll talk about later today. So that's fun. And then, given that that's our goal, we want to write these down in ontologies so that everybody uses the same term for the same meaning. And SemGen is the tool support for doing it. So I'll say one slide about the OPB, the Ontology of Physics for Biology. It really does help to think about things this way. There are either, in the world, there are either things or things that happen over time, processes. And of the things, there are physical entities that are often like calcium ions, versus properties of those things, like mass, charge, volume, amount. And then there are dependencies amongst those properties that are the equations. But physical entities participate in processes, things that unfold over time. And the properties, the volumes, the pressures, are trajectories over time that are part of that process. So a composite annotation uses these players to mark up some variable in a biosimulation model. So when I talk about annotations, I'm generally not talking about model-level annotations. That is real metadata, like who is the author, when was this published, broadly what is this equation, what is this system about. Instead, I'm really talking about individual variables. A particular portion of blood, or a particular chemical ion, would be the physical entity that you're talking about. And you might be measuring blood pressure or chemical amount, moles. And you might care that the blood is in the aorta or that some ion is in some region of the cytosol. So the key about a composite annotation is you're drawing from more than one ontology because you're talking about things as well as processes as well as properties. So that's the key difference. Is for example, in SPML models, things are often annotated with species, but that's just the thing. It doesn't talk about whether it's a chemical concentration or the charge. It's kind of all I'm going to say about composite annotations. Is that okay? So then a little bit of results. This is results that were presented, I believe, here, some published back in 2008, where they put together 3 models: the bioreceptor, a circulation model, and a smooth muscle cell model, and combined these Annotations automatically emerged into this thing, and then we're able to run it in JSON. You can see that publication. But for this conference, one of the things we did, and I'm quite excited about, is we took this publication in 2008 by folk outside of it. And we had no idea about these people that were from this strange place down under. We tried to reproduce it, and it was successful. Okay? So these are 3 models and an engineer that were published prior to this publication. Okay? And then this publication were these folks putting 3 models together and showing that the combination was better or more useful or more interesting than the solitary one. So we did that as well, and we used our Sengenesis to do that. So we had the 3 source codes in CellML, we annotated them with composite annotations, we merged them, we created a merged model. You know, this is a semi-automatic, but not fully automatic process to do that. And then we're able to output either in JSON or CellML. Because we've represented the underlying semantics, the underlying equations, we don't care what output format it is. And so then, as we did in 2008, we can take the JSON model and run out a JSON biosimulation model. And we can also take the CellML and run them open. It's obviously impossible. What I found out 3 days ago was that at this time, this publication, 2008, predates OpenCore. And so they actually never ran the combined CellML model. They ran the MATLAB model and demonstrated that it did better. Whereas we, for the first time ever, have taken this merge and running it directly through the simulation engines, the simulation engines that are designed for CellML and JSON. Pretty cool. Finally, I mentioned V3, so this is what this looks like. This is what's cool to see in a live demo, is you can visualize various models. Each dot is a variable annotated, and the arcs are the mathematical dependencies amongst them. So this is connecting volumes and flows in a closed-loop circulation model. Okay, my final point is, okay, so we've done it. We've got annotation. We can do that with this tool. We can visualize the models. We can search and retrieve and piece them together and extract. Is everything happy? No, because we still haven't convinced outside users. That is actually the main goal of our new collaboration with the DPR. We've connected up with this big project that has lots of mathematical modelers. And our idea is we're actually going to get them to use the tool. So we're going to see how useful our approach is. And we can only test this to get outside users, like at the DPR and this community. Okay? So, please try it out. Download Sengenesis 3.0. There's that. I'm looking for feedback and for understanding how useful this is or isn't for model merging and model visualization. We will actually carry out a formal evaluation of the tools toward the end of this year. And you can ask me more about that. Didn't look at a clock and I'm not ahead or behind, but that's the conclusion. This is hard work. I think we're quite brave in that we're going outside of our own shop to recruit users and try to understand how DPR people use it. It's a step that's very important. We think constraints are hoping for outside. There's all people. I think Max is on. Max is on the way. Yeah.
So that's great. I really enjoyed the review. Do you have a group of people that are now going to start building composite annotations?
Yeah, I didn't put that slide up. So Graham and Chris, no, not Graham, Chris and Ryan and Max. Now, Chris and Max and Brian have spent the last 2 months or so annotating 25-odd models with composite annotations from the CellML library. If this was my machine, I could bring it up. I don't have the list with me. 25 models. We picked we talked to Mike about which models, we sent him the list, and so those models are now fully annotated. Now, of course, as I just talked about in discussion, we keep those annotations separate from the source code right now.
So I guess what I'm getting to is, as you carry on in that process with more and more models, you're building a database of these composites.
Yep.
And presumably you'll start to find that the number of new ones
yes.
substantially.
Yes.
And I guess what I wonder is how long before we got reasonably comprehensive set of all of our information.
That is an interesting empirical question, right?
Yeah.
I think
at that point, it makes it a lot easier for people using open form to say, access your database and know that there's going to be the information.
To some degree, it depends on the variety of models. Right? If we always stuck with a particular class of models, we'd reach that point much quicker.
Can we send you requests to look at particular?
Yeah, please. Yeah, I was kind of hoping Mike was doing that, but yeah, talk to him, whatever. Yeah, send us the models you would like us to annotate. We'll try to do those.
And one thing that's interesting, so Max did have a tool in there. If you're annotating something and there's the exact same variable name in another model, or let's just say you have a model that has an endocardial version and an epicardial version, then you can actually port all your annotations, just annotate one, and you can port all those annotations to the other version of that. So it'll annotate everything, and then you just have to pluck out a few that maybe weren't annotated, or the new things that are in that other version of the model. So what I'm getting at there, as we develop this larger kind of grouping of annotations, you're going to be able to go in there and find the annotation you need rather than make them all on the fly.
I mean, I didn't demonstrate the annotation tool, but it's really quite intelligent.
I'll do that a little bit tomorrow.
Are you giving a unique identifier for each component?
Yes. Well, so this is in the OWL framework, so everything has a URI. So in that sense, yes. But we're also keeping track of each part of the composite annotation, right? So that if something else comes along, so your question could be difficult to answer.
Yeah, what I'm trying to get is how to facilitate reuse.
Right. So that's what I was trying to answer. We also understand the composite as pieces, and so if another model comes in with, suppose you've got 3 ontologies, another model comes in with 2 of them, it might suggest there's a similarity there. Yeah.
Thanks, John. Last year when I was trying to use Engine, OPP was the rational basis for composite annotation.
Right.
And so I didn't have problem for physical entities, but for example, something like rate constant,
right.
Because I think it's categorized as physical dependency, so I couldn't use OPP.
Right.
I could find the word SPO. So do you have something in your new version to be able to
Yes, we talked about this offline. We have the version used definitely was behind this one. So there's several ways around that. First of all, you can create custom annotations that do not refer explicitly to any ontology. So I think that's probably what you want to do. But beyond that,
if I don't want to use custom,
what do you want to use then?
like for if I have rate constant,
Right.
Because I contacted Maximum, and he was thinking maybe we don't need to annotate these parameters in the models.
Right. So Brian will talk about this more tomorrow, about what things to annotate and what things to do. So one of our philosophies here is that we're trying to build a Lego plug-and-play thing. So actually, we take the position that you do not want to annotate it, because you only want to annotate those things that an outside user would want to see if they're interested in sharing. They want to know all models that have text. They don't care about the particular parameters. I'm not the expert, but there's at some point a place where you don't want to know the details. You want to do some information hiding. And so you should stop there and not annotate. So maybe that's what Max was getting at?
I mean, I can see that there's, at some point, you're not searching to see what has a rate constant of a certain value or something, or a rate constant that's in this, that's going to be a property of a dependency, or some sort of a way of describing the process. So what you really need is the word for that process.
Right.
And so that's, and these are just a lesson of work. We're adhering to that 10. Let's go down to this level and see where, if we run into trouble, then we'll start opening that up.
Okay. Thank you, John. Okay. So we're running a little bit late, but we've got plenty of time for lunch. I'm going to be really quick. So I was just going to give an update on where things are at with some of my own code. And the basic idea is trying to create a suite of tools, essentially for modeling epithelial cell transport. In doing this, we want to create a library of reusable models or templates for generic processes and make them available using all these tools that we've just heard about this morning. Okay, and use standards, use the repository, everything's versioned and everything, so it makes it easy to do stuff. And not just the models, but we want to do the same with experimental protocols. So you can make your protocols, your simulations available in the same way that we already make models available, annotate them. And if you have data, and we'll talk about how this all plugs in with CellML later on today, but making it all available so that when you make new models, you can test against existing data and make sure your models behave as they should. So the main thing that's changed since I talked about this last year is the URL. And that's pretty much the only update. So it's called GET, Generalized Epithelial Transport. So it's a collection of different utilities and these sort of models that already exist that you can pull together. And as we just heard, and as we'll hear more tomorrow, we want to start making use of these annotations and hopefully just making use of the tools to do all the merging and things like that for us. But we need this sort of collection of models to be available. There's several different tools that I'm working on. There's the creation, which is sort of more focused on the CellML side and how you can pull sort of CellML models together based on your knowledge of those models. And so it's slightly different to the way CMGen's doing their model merging, but hopefully complementary, and as things evolve, we'll come together in the middle somewhere. So the idea is to be able to allow users to rapidly create custom models for whatever their specific investigation is. And at the moment focused on sort of web-based tools that you do this. And this is done currently because we know the models that are available in the library and we know how to use them and what to do with them. So it makes it quite easy. So if you add a new membrane transporter, you just know what it's transporting and to add that to your sort of flux motion model. And so while you can encode epithelial cell models in CellML as it is, and just plug it into OpenCore and run simulations, that sort of gives you a limited flexibility for what you might want to do with epithelial cells in particular. So there's this algorithm published in 1984, quite old now, but it still seems to work well. And it's a bit more flexible, and by using our knowledge of your CellML model for the epithelial cell, you can do some fancy things with it in terms of electroneutrality, mass conservation, and those sorts of things. So dissemination, basically putting things in the repository and putting it out there. So you want, you know, as I said, little modules that you can assemble together into bigger modules, and the bigger modules, plug them all together, annotate them so that people can understand what they are and use them appropriately, or not, but know that they're not using them appropriately. And you put it all in the repository. So just a couple of examples that I don't think Tommy showed this morning. We have sort of this workspace that we can't read, but basically it's a collection of generic processes, maybe. And we now have a few of these examples where we've annotated them using sort of Uniprot IDs, so you can link through to the actual definition of what that transport protein is. If you can read it, you can see, you know, where it's spatially located. These are renal nephron cells, so they're all in the nephron. And so there's a few of these examples in the repository now with this extra information. So if you want to have a look, I can show you the URLs. We probably can't read them. And as you know, normally you get the pretty pictures and stuff. So the other side of this, we've got these utilities, but then I've also been working on a sort of prototype server-side services that exposes these utilities through standard web services. And this started out as me just having a play with some cool technology, but other people are actually starting to use it. So it's a real pain to have users. They want things to work. So just as an example, so because it's all based on standards, it's applicable sort of to a wider range of problems than just epithelial cells. So here's an example. It's been around for a while now, but there's this open physiology website that Bernard DeBono is running with the F anatomy sort of web interface. And so essentially what you can do is you can say your region of physiology that you're interested in. And then you can query for the specific terms, go to the repository, get back some results. And they say, oh, here's a model that does what you want. So you can now sort of using one model server services, load that model in, and essentially using the same interface that Jim described for his work. You know, you can control variables in the model, run simulations, and get outputs. And so this is now sort of being pulled together with some of Sarusha's work, looking at circulation and blood flow around the body. So I'm not sure how much is actually on the website, but the basic ideas are described there. So what I'm currently working on is trying to wrap this up in full user interfaces that people want to use. And working at this higher level, as Peter said, we want biologists to want to use these tools, and also spreading beyond just a single cell. So that's the basic concept that we're working towards. You have a nephron, some sort of finite element model, and you want to say sort of anywhere in your model, you know, somehow drag and drop or whatever, say this type of cell goes here, and within your cell you want to use this transporter, and just make it easy for people to do that. So just quickly, support from all those people, those groups.
So GMS could be used within Alan's HTML right-hand window to retrieve a model that you could then directly dump into OpenCore. Right? When you, if you wanted to access, you could use your web services setup to now be able to load models directly into OpenCore without having to go through the process of copying into the lab.
It could, but it's. I mean, I saw the GMS stuff as a sort of prototype for what you'd really want DMR to provide. But yeah, it's just standard web services that you can access. Yeah.
It probably wouldn't work so well on Windows because you have to run a local web server, multiple web services, which is not great on Windows with local hosts. Or block you. Well, if you do Linux and Mac, not always.
Yeah, so
Different technology.
I think for a tool like OpenCorpus, GMS is essentially doing most of that in the background, whereas OpenCorpus is nice to do that. So. Yeah.
Try something to drop the server to do the work of what everything do in itself, trying to get to find this model and returning the result. No, visualize that result, not doing any work.
I suppose I'm just looking to the situation where you're running open core, you want to go to the PNR, grab a particular protein you need to put into your server to SLM. It comes with all the model and metadata, etc. So we're talking for mechanisms to increasingly move to drag and drop environment or grabbing from the library of models in PNR.
Yeah, so if OpenCore was providing essentially that web front end, that would make sense. But for the running somewhere.
Yeah, that's all.
Yeah.
It's still be running locally.
Yeah. Any other questions? Okay, so we're still half an hour behind. So we had a long lunch break, so we might make that a shorter lunch break and still aim to come back at 2 o'clock. And hopefully food will be out shortly. Thank you. This from before recognized that it comes.
And then you have the